Hello students, welcome back. So we are basically covering a very important chapter, that is chemical kinetics. Now I hope you have gone through the lectures that have been delivered till now. So till now we have covered the very basic concepts of molecularity, order, what rate of reaction is. Then we went on to derive the integrated rate law for a zero order reaction. We did some examples of zero order reaction. I hope you have memorized all the examples of zero order reaction. Then we went on to write the differential rate law for a first order reaction, and then we wrote the integrated rate law for a first order reaction. And in the previous lecture we were doing some very good questions on first order gaseous reaction. Okay, so this is the portion that we have covered till now. Anyone who has missed any of those lectures can go back in the catch up videos and see those lectures. And I hope you are solving your daily practice problem sheet as well. Okay, so in today's lecture we are basically going to focus on how do we experimentally determine rate laws. There are some basic methods through which we determine these experimental rate laws. So let's start the lecture. Okay, so the first method is called as initial rate method. Okay, now what do we understand by initial rate method? Okay, I will show it through some example, and we are going to solve some good level problems on this as well. So basically what we say is, in this method we vary the concentration of one of the reactants and the other we keep it as a constant. Okay, suppose we are having two reactants, say we are having A and B, okay, and this is reacting in certain reaction and it is forming say C and D. Okay, we don't know the order with respect to A and B, so we are basically going to write the rate law expression for this particular reaction using the method of initial rate method. Okay, so what we will do is, suppose we take some concentration of A. Okay, suppose we write it as A naught. Okay, and suppose the order with respect to A is X. Okay, and suppose we take the concentration of B as B naught. Okay, and the order with respect to V, let us suppose it is Y. Okay, so basically we are going to get a rate on this expression. So what we are going to do experimentally, we are going to take certain amount of A and certain amount of B, and we are going to carry out the reaction, and we are going to calculate the initial rate law. Okay, now what we will do is, we will keep the concentration of any one of the reactants constant, and we will vary the concentration of the other. Suppose in this case, okay, we vary the concentration of A. Suppose we take the concentration as A1 and we keep the concentration of B as B naught only. Okay, so we will get the new rate law expression something like this. Okay, so basically what we are doing, we are taking the reactants, okay, we are keeping the concentration of one of the reactant constant and changing the other. Okay, so we are going to write the rate law based on those concentration. Now if you look at these two expressions, if we just divide 1 and 2, okay, so what we will get, Rho upon R1, that is rate initially upon the new rate when we change the concentration of A to A1, keeping the concentration of B as B naught only. So because it is a same reaction and the rate constant would be a constant, it changes only with change in temperature. Okay, so this will basically get cancelled out. Now because these two quantity, the concentration of B are same, so on dividing they also get cancelled out. So we are basically left with A naught and A1. Okay, so this will be A naught upon A1 raised to power x. So we are basically dividing these two equations and we will get this expression. So from this we can calculate the value of x. Suppose we take log over here. So this will be log of R naught upon R1. This will be equal to x into log of A naught upon A1. Okay, so if we take log, so x we can take it out. So basically x will come out to be log of R naught upon R1 divided by log of A naught upon A1. So this is how we are going to experimentally find order with respect to reactant A. Now suppose we want to find out the Okay, suppose we want to find out the order with respect to B. So what we'll do, we'll keep the other reactant, that is A. Okay, we have already find, okay, suppose we want to find the order with respect to B. So we'll change the concentration of B, but we'll keep the concentration of A constant. So basically let us take the concentration of A as A naught, and at that time we take the concentration of B as B1. So now suppose the rate becomes R2. So basically if you divide R1 by R2, okay, so if you divide R1 and R2, you will get B naught upon B1 raised per Y. So basically in the similar manner, Y can also be found out by using this expression. Okay, so in this way we are going to find X and Y, which is rate with respect to A, order with respect to A, and order with respect to B. So basically what we do in the initial rate method, we vary the concentration of one of the reactants. Okay, so in the initial rate is determined by varying the concentration of one of the reactants while the others are kept constant. So we'll continuously change the concentration of one of the reactant and other we'll keep constant, just the way we are doing in this. Like we have initially taken suppose A naught amount of A and B naught amount of B, so that will correspond to a particular rate. Okay, now what we'll do, we'll vary the concentration of one of the reactant keeping other as constant. So we take the same amount of B, but now we are taking a different amount of A. So we'll write the new rate expression. Obviously the rate will change because the concentration is changing. Now we'll divide the two, the common factor will get cancelled out. So in this way we are going to get order with respect to one of the reactant. Similarly the same process we will repeat it for the second reactant. Okay, so we'll change the concentration of B and we'll keep the concentration of A as constant. So we'll get a new rate, say R2, then we again divide, say we divide R naught upon R2. So basically this is R naught upon R2. So A naught and A naught get cancelled out. So basically we are left with B naught upon B1. Okay, so this is the way we calculate Y. Okay, so this way we can calculate rate with respect to A and rate with respect to B, and the overall rate would be X plus Y. So the value of order with respect to a reactant can be determined by taking the ratio of the rates. Okay, so I hope this is clear to you. We'll explain it through some examples as well. So just write it down. So this is how things are done experimentally. We are mixing two reactant. We'll mix the reactant in a certain amount. Suppose we mixed A1 amount of A with B1 amount of B. Okay, and we'll record the rate with that particular concentration. Then we'll keep the concentration of one of the reactant constant. Say suppose we keep the concentration of A as A1 only. Okay, and we take the concentration of B as say B2. Okay, so we'll get the new rate. We'll just take the ratios. So one of the term will get cancelled out, and we can find rate or we can find the order with respect to the other reactant. Similarly, we can repeat it for the other reactant and we can calculate the order with respect to that reactant as well. Okay, so this is a very basic method. Okay, so just look at some questions on it. So just read this question first. So basically it is saying that there is some gaseous reaction in which A2 is reacting with B2 and forming 2AB. Okay, we don't know the rate equation or the rate law for this particular reaction. The following rate data were obtained at 300 Kelvin. So basically rate of disappearance of B2 was reported to us, okay, and the concentration of A and B2 was reported to us. When the concentration of A was 0.015 and the concentration of B2 was 0.15, the rate of disappearance of B2 was 1.8 into 10 raised to minus 3. Okay, when we change the concentration, the different rate of disappearance of B2 was given to it. Okay, so the question says calculate the rate constant for the reaction and the rate of formation of AB when concentration of A and B2 is given to us. Okay, so what we'll do in this, first we'll assume that let the rate law be rate is equals to K into concentration of A2 raised to our factor say P and concentration of B2 into raised to power factor Q. So basically P is the order with respect to A2 and Q is the order with respect to B2. So now what we'll do, we have been given 3 data, we'll just plug these data in this equation, okay, and we'll get 3 more equations. So basically if we put rate as 1.8 into 10 raised to minus 3, we know that the concentration of A is 0.015 raised to power P into concentration of B2, which is 0.15 raised to power Q. Okay. Similarly, if we write the second equation using the second data that has been given to us, we know that the rate is 1.08 into 10 raised to minus 2. Okay. The concentration of A is given as 0.09. So this is raised to power P into concentration of B2 raised to power Q. Okay. Similarly, we will write the rate according to the third data given to us, which is 5.4 into 10 raised to minus 3. This will be equal to K into concentration of A is given as 0.015 raised to power P into 0.45 raised to power Q. So basically we have established 3 equations. Now we are going to divide these equations and calculate P and Q. So if you look at this reaction, if you look at the equations closely, suppose if we divide say 1 with 3, okay, so we are dividing 1 with 3. So basically if you look at this, the concentration of A2 in 1 and 3 are same. So basically in this, the concentration of A2 has not changed, but the concentration of B2 has changed. So this will be basically 1.8 into 10 raised to minus 3 divided by 5.4 into 10 raised to minus 3 equals to K into 0.015 raised to power P into 0.15 raised to power Q divided by K into 0.015 raised to power P into 0.45 raised to power Q. Okay. So if you look at this, these two quantity will get cancelled out. Okay. So basically we are left with, this is 1 by 3, this will be equal to, this is also 1 by 3 raised to power Q. Okay. So this is basically 1 by 3 raised to power 1 and this is 1 by 3 raised to power Q. So the value of Q will come out to be 1. Okay. So the order with respect to B2 is 1. Similarly, if you look at the data, if we divide say 1 and 2, okay. So if you divide 1 and 2, you can easily see that the concentration of B2 is not changing, okay. The concentration of only one of the reactant, that is A2, is changing. So when you divide 1 and 2, so basically we get 1.8 into 10 raised to minus 3. Okay, I can write this as 10.8 into 10 raised to minus 3. Just I have done that so that the factor becomes equal, so that we can cancel out easily. This is basically K into 0.015 raised to power P into 0.15 raised to power Q divided by K into 0.09 raised to power P, okay, into 0.15 raised to power Q. So these two terms will get cancelled out, K and K gets cancelled out. So basically 10 raised to minus 3 and 10 raised to minus 3 gets cancelled out. So this is basically 1 by 6. Okay. So 1.8 divided by 10.8 is 1 by 6. Okay. And this will be basically 15 upon 90. Okay. So this is basically also 1 by 6. So this is 1 by 6 raised to power P. So if you can clearly see that the value of P will be equal to 1. So we will say that order with respect to A2 is also 1 and order with respect to B2 is also 1. So we will get this as the equation. Okay. Now the question says calculate the rate constant for the reaction. Now because we have already calculated the order of the reaction, we will use any of the data to calculate the value of K. So suppose we take the value given in data 1. So this is basically 1.8 into 10 raised to minus 3. This will be equal to K into concentration of A2 is 0.015 raised to power 1 into concentration of B2 is 0.15 raised to power 1. So we can find out the value of rate constant. Okay, so this is very simple concept. So we will get the value of rate constant. Okay, so the first question says calculate the rate constant. So the rate constant will be 1.8 into 10 raised to minus 3 divided by 0.015 into 0.15. Now the second question says, and the rate of formation of AB when A is 0.02 and B2 is 0.04. So basically rate of formation would be K into concentration of A2 raised to power 1 into concentration of B2 raised to power 1. Okay, because this is the rate equation, so rate of formation would be this. So we know the value of K from here. Okay, so we can calculate K from here. So we know the value of K. A2 concentration is given as 0.02, B2 concentration is given as 0.04. So you just have to put the value and multiply, and you will get the answer. Okay, so just have a look at the question. I hope this question is clear to you. Now just one thing which you should always see over here is you have been given rate of disappearance. So basically this data has been given to us. Rate of disappearance of B2 would be this. This is given as 1.8 into 10 raised to minus 3. This is also the overall rate because the stoichiometry of B2 is 1 only. Okay, so this is also the overall rate. If suppose there was some quantity over here, suppose there was a stoichiometric number say like 3. So you have to divide this by 3. Okay, I hope you are understanding this because this is in terms of rate of disappearance, because in this case stoichiometry is 1, so the overall rate is also equal to the rate of disappearance of B2. So these are the small point that you should take care of, because in IIT these are the only small points where questions are created and students make a lot of silly mistake in that. Okay, so just write it down, or you can take a snapshot of this question. Okay, so I hope you have taken a snapshot. Now just try to solve this question. Okay, take 3-4 minutes. Basically a reaction has been given to you between mercuric chloride and potassium oxalate. Okay, the mass of Hg2Cl2 precipitated from different solutions in a given time at 100 degrees Celsius was as follows. Okay, so when initially the concentration of HgCl2 was this, K2C2O4 was this, and after 65 minutes basically the moles would have been here. Okay, the moles of Hg2Cl2 precipitated was 0.0068. Okay, so basically we have not been given rate. Okay, so basically we have been given moles precipitated and time. Now we know that rate is always, okay, the unit of rate is, yes, the unit of rate is moles, okay, or molar per liter, that is mole per liter per second. Okay, so we will assume that the reaction is happening in a 1 liter container. Okay, so basically I am going to say that the rate of this reaction would be moles per liter per minute. Okay, that is molar per minute. So basically if you just plug the data, so the rate would become 0.0068 divided by time, that is 65 minutes. Okay, so this would become the rate. Okay, that is moles precipitated upon time taken. Okay, stoichiometry is 1. So again the rate of appearance would be same as that of overall rate. So this will be rate 1. Similarly rate 2 would be 0.0031 divided by time taken, that is 120. Similarly rate 3 we can write this as 0.0032 divided by time taken, that is 60 minutes. Okay. Now suppose this reaction was given to you, we want to find out the overall rate. So we will write the rate equation as K into concentration of HgCl2 raised to power say A into concentration of oxalate raised to power B. Okay. Now we will just put the different datas in this particular expression, we'll divide and we'll get the value of A and B. So if we put the first data, okay, the rate for the first data was this, so this would be basically K into 0.0836 raised to power A into 0.404 raised to power B. Okay. Similarly, if you look in the second data, the rate was this, so this will be K into 0.0836 raised to power A into 0.202 raised to power B. Okay. Similarly, for the third data, the rate was this, so the concentration of HgCl2 is 0.0418 raised to power A into concentration of K2C2O4 raised to power B. So we get three equations. So basically we are just putting the data in the expression, assuming the order with respect to HgCl2 be A and with respect to K2C2O4 be B. Okay. So you can clearly say if we are dividing 1 and 2, if we divide 1 and 2, so basically in this the concentration of HgCl2 is remaining constant and the concentration of K2C2O4 is changing. So if we divide this, so we will get 0.0068 divided by 65. Okay, when you divide by this, so this is basically 0.0031 into 120. Okay, this should be equal to, these two terms will get cancelled out, so this will be basically 2 raised to power B. Okay, when you do the calculation, you will get 4 over here, so 2 raised to power B is equal to 4. So we can write this as 2 raised to power 2. So well, value of B would be 2 in this case. Okay. Similarly, you can divide data 1 and 3. Okay. If you divide 1 and 3, you can clearly see that the concentration of K2C2O4 is same. So when you divide it, the concentration term of K2C2O4 will get cancelled out, HgCl2 will be left. So basically we will be able to calculate the value of A. So when you divide 1 and 3, so we are basically getting 0.0068 divided by 65 into 0.0032 into 60. Now we know that these two terms will get cancelled out and this is basically 2 raised to power A. So when you do this, I think this will come out to be 2. So the value of A would come out to be 1. Okay. So the rate of this reaction would be K into HgCl2 raised to power 1 into concentration of K2C2O4 raised to power 1. So the overall order of this reaction would be 1. Okay. So I hope you are getting this question. They are actually very easy question. Always a rate data would be given to you. You have to assume order with respect to one reactant as certain quantity and order with respect to the other reactant as certain quantity. Now just we have to put all these, plug these data, okay, in these equations. So we will get 3 equations. You have to divide in such a way that one of the terms get cancelled and we are able to find out the value of the other variable. Okay. I hope this is clear to everyone. Only thing which you should note over here, what rate data has been given to you. If it is rate of appearance or rate of disappearance, you have to make sure that you are dividing it by stoichiometry so that it becomes overall rate. Okay. And if suppose rate has been given directly to you, so that is again a very simple question. Okay. So you can have a snapshot of this, you can solve it by your own. Okay. So let me take you to one more question on this. Okay. So just look at this question. This was JEE Advanced 2019. Okay, that means like the last year paper only. So just have a look. We have been giving a kinetic data where a reaction A plus B plus C is changing into some product, okay, and some concentration value of A, B and C is given to us and rate of reaction has been given to us. Okay. So basically we don't know order with respect to A, B and C, and that is why these data has been given to us, because there are 3 unknown orders. So 4 data has been given to us. We will find the order with respect to each of the reactant Okay, so the first task is to find out the order with respect to each of the reactant. Okay, so we'll just assume the rate to be equal to K into concentration of A raised to power say X, B raised to power Y and C raised to power Z. Okay, so X is the order with respect to A, Y is the order with respect to B and Z is the order with respect to C. So what we are going to do, we are going to plug the data that has been given through experiments in this expression and we are going to get 4 expressions. So let us put the first data. So when we put the first data, the rate has been given to us as 6 into 10 raised to minus 5. This will be equal to K into concentration of A is given as 0.2 raised to power X into 0.1 raised to power Y. The concentration of C is 0.1 raised to power Z. Okay. Now let us use the second data. Again the rate is given as 6 into 10 raised to minus 5. This will be equal to K into 0.2 raised to power X. The concentration of B is 0.2, so 0.2 raised to power Y and the concentration of C is 0.1. So clearly you can see that the concentration of A and the concentration of C in both the cases is same. So basically we are changing the concentration of B by keeping the concentration of A and C as constant. So we'll just divide 1 and 2. Okay, so basically this when you divide you get 1, these quantity get cancelled out. So basically we are left with 1 by 2 raised to power Y. Okay, now we know that this is 2 raised to power minus Y, 1 can be written as 2 raised to power 0. Okay, so we can say that order with respect to Y is 0. Okay, so we got one quantity. Now let us write the third equation. Okay, now the rate for that has been given to us as 12 into 10 raised to minus 5. I am writing as minus 5 because all the rate were in the factor of 10 raised to minus 5. So this is basically 12 into 10 raised to minus 5. Concentration of A was 0.2 raised to power X. Okay, the concentration of B is 0.1 raised to power Y into concentration of C which is 0.2 raised to power Z. Okay, so what we are going to do in this, if you look at the first and the third data, okay, the concentration of A 0.2 and 0.2 remain same and the concentration of B remains same. Okay, so if you see the concentration of A in the data 1 and data 3 remain same and in the concentration of B again the data 1 and data 3 are same. So basically if we divide 1 and 3, so we are going to get half. This will be equal to this and this term get cancelled out, this and this term get cancelled out. So we are basically left with half raised to power Z. So in this case again we get the value of Z as 1. Okay. Okay, now since we have got the value of Z and Y, you can directly use any of the equation and get the value of X. Okay, or you can write the fourth equation. Okay, now in examination when this is coming, when this kind of question is coming in exam, so you have to make sure that you are doing it very fast. Okay, so you can either plug these value in this expression and get the value of X, but we don't know the value of rate constant over here. Okay, and the rate constant has not been given to us as well. So basically we have to again use the equation only. So basically this is rate is 9 into 10 raised to minus 5. Okay, and the concentration of A is given as 0.3 and the concentration of B is given as 0.1 and the concentration of C is given as 0.1. Okay, so if you look at the first data, okay, the concentration of B is same, the concentration of C is same, only the concentration of A is changing. So basically if you divide 1 and 4, so we are going to get 6 by 9. Okay, this is equal to 2 by 3 raised to power X. Okay, so this is also 2 by 3 only, 6 by 9 is 2 by 3. So this is basically 2 by 3 raised to power 1. So X will be 1. Okay, so we quickly got the rate law. So the rate law would be K into concentration of A raised to power 1 because X is 1, B raised to power 0 because the order with respect to B is 0, and C raised to power 1. Okay, so we derive the rate law. Now the question says the rate of the reaction for A is equals to this, B is equals to this, and C is equals to this is found to be 5 into 10 raised to minus 5. So what we are going to do, first we are going to calculate the value of K. So we will use any of the data, suppose we use 1, okay. So basically from this we are going to calculate the value of K, okay. So we know that the value of X is 1, the value of Y is 0, so anything raised to power 0 is 1, and the value of Z is also 1, okay. We have already calculated this, okay. So we are going to get, this will be 10 raised to minus 2, so these factor would lead to 10 raised to minus 3, and this would come out to be 3.25. So basically we would get the value of K as 3.25 into 10 raised to minus 3. You can also write the units, which will be per molar per second, okay. Now we have got the value of K, so basically we have to find the value of rate when the concentration of K is this, when the concentration of A was 0.5, so I can write this as 1.5 into 10 raised to minus 1, and the concentration of B 0.25, because it is 0 with respect to B, so anything raised to power 0 would be 1, so we don't take care of the concentration of B. C is 1.5 into 10 raised to minus 1, okay. So 10 raised to minus 3 into 10 raised to minus 1 into 10 raised to minus 1, so basically this is 10 raised to minus 5, okay. So basically you have to multiply these terms, so this is basically 3.25 into 2.25, okay. So just you have to carry out this calculation, and this is the value of K, okay. So this, you can believe, this is the level of JEE advanced questions. They are not difficult at all. They are basically attached with the basic concept, but somehow we just mess it up and we think that mains is different, advanced is different, okay. Both of them have, like, we have to read the same theory only. In JEE advanced we have to do a lot of solving, do a lot of calculation, but they are not at all difficult, okay. So you can see this question, this was in 2019, so a very direct question that came from the rate law data, okay. So you can take a snapshot of this as well, okay. So I hope this question is clear to you. So basically in such cases what we are doing, we are varying the concentration of one of the reactant and keeping the other constant, and then we are dividing the rate so that we can get order with respect to that particular reactant whose concentration which we are changing with respect to time, okay. So I hope this is clear to you. So now let's get back to the okay. So the second technique or the second method to get the experimental rate law is the use of integrated rate laws, okay. Now we have already derived the integrated rate law for a zero order reaction, which was A naught minus AT was equal to A naught minus KT. So basically the plot of A versus T would come out to be linear, and the slope would come out to be minus K, and intercept would be A naught, okay. For a first order reaction, we have already derived the integrated rate law. We say that KT is equals to 2.303 log of initial concentration upon final concentration. So when you plot it log A versus T, we get a slope of minus K upon 2.303 with a intercept of A naught, log of A naught. For a second order reaction, we derived in the last class. So that is 1 by A equals to 1 by A naught plus KT. So when you plot 1 by A with T, okay, we will get K as the slope and the intercept would be 1 by A naught. So we have done all these plotting of the graph in the previous lecture. So basically in the integrated rate law, what we have to do, we have to be just use these equations. So this is basically a hit and trial method, okay. So suppose data has been given to you. For each of the data, suppose we are using the zero order equation, okay. Suppose 5 or 6 data has been given to you. For each data of the concentration that has been given to us at different time interval, we'll plug the value of initial concentration and different concentration of A at different time, and we'll calculate the value of K. for if, okay. So I hope this is clear to everyone. Suppose there are like 3 data given to us at different time interval, at different time different concentration of A was given to us. So we know the initial concentration. Suppose we assume it to be a zero order reaction. So what we'll do, we'll keep on like at different time we'll keep on using the different concentration data and we'll keep on calculating the value of K. If the value of K at different time intervals comes out to be same, it means that the reaction was following zero order reaction. So this is basically a hit and trial method. A data would be given to you at different time interval, okay, the concentration would be given to you at different time interval. So what we are going to do, we are going to use any one of those equation, okay. Suppose we use zero order reaction, okay, we use this integrated rate law equation for a zero order reaction, okay. So for different time the different concentration of A would be given to us. So we'll calculate K at all different times. If the value of K comes out to be same at different times, that means the reaction is a zero order reaction, okay. But if it doesn't come out to be same, that means this hit and trial method didn't work. So we'll use the first order equation now. Now at different time we'll like keep on changing the concentration of A and we'll keep on calculating the value of K, okay. If the value of K at different time interval comes out to be same, that means it is again a first order reaction. If it doesn't come, that means it is not a first order reaction, then we have to use a second order equation integrated law, okay. So in this again at different time the concentration of A would be given to us, we would know the initial concentration. At different time we can calculate the value of K because the concentration of A would be given to us at different time interval, and if the value of K comes out to be same, okay, for different time intervals, that means it is following a second order reaction. So this is a little tedious method, okay. So this is basically a hit and trial method where we are assuming the reaction to be of a particular order and we are directly using its rate integrated law and we are plugging the concentration value at different time interval and we are getting the calculating the value of K. If K comes out to be same, okay, that means the reaction is inconsistent with the particular rate law, okay. So just look at one of the question to understand this. This was asked in IIT 2010, okay. So this is basically a question says the concentration of R in the reactant changing into product was measured as a function of time, okay, and the following data were obtained. What is the order of the reaction, okay. So again this is basically a hit and trial method only. We don't know what to be, which formula to be used. So I will start with zero order, okay. For zero order we know that the equation is A naught minus AT is equals to KT, okay. So at different time the value of the concentration of A has been given to us. So at different time we are going to calculate the value of rate constant K. So we know that. So first we will calculate for 0.05 minutes, okay. We know that the concentration of A at t equals to 0 is 1, okay. So this is basically 1 minus, we know the value of the concentration at time 0.05 second, which is 0.75. So this is going to be 0.05 into K, okay. So this is basically 0.25, this is equal to be 0.05 into K. So K is basically 5 in this case, okay. So this unit will be moles per liter per minute, okay. Now we will calculate the rate constant K at time 0.12 minute, okay. So we are again going to use the same zero order equation. So the initial concentration is 1, the final concentration at time t equals to 0.12 is 0.4 and this is again equal to 0.12 into K. So this is basically 0.6, this is equal to 0.12 into K. So K will again come out to be 5, okay. So for these two time interval K has come to be same, okay. So we are going to calculate it for 0.18 minutes as well. If the value of rate constant K again comes to be same, it means that this reaction is following a zero order kinetics. So let us just try for 0.18 minute only. So we know that the value initial concentration is 1, final concentration is 0.1, okay, and the time is 0.18 minutes. So again the value of K would come out to be 5, okay, because at different time interval the value of rate constant using the zero order integrated rate law came out to be same. It indicates that the reaction was following a zero order kinetics. So basically order of this reaction would be 0, okay. So in this case we were lucky that we got this value in the first trial only, okay, because if the zero order equation was not valid, the value of K would have come out to be different at different times, okay. So for that again we have to try it for a first order reaction. So basically first order reaction K was 2.303 upon T log of A naught upon AT. So again plugging these value at different time, we will get the value of rate constant at different time. If it came out to be same, it indicating it is a first order reaction. If not, then try for second order reaction. So this is basically tedious, but I have seen through my experience in JEE mains and advanced, basically the questions are either from zero order or first order, okay. So I hope this is clear to everyone. So if you look at the IIT-JEE problems, they are not difficult at all. Someone who says that IIT-JEE is difficult, I don't think he is like telling you correctly. It is not difficult. It is basically a practice of good level problems that will help you in understanding those concepts well, and then reading a good book like NCERT or some any other book which actually helps you in retaining all those content. A good level of practice, a good level of dedication is required. That's it. It's not difficult at all. The chemistry paper in JEE Advanced is always very easy as compared to physics and mathematics. Only thing needed is a very good idea about the topic, a good level of problem solving, a very good and a crisp note that will help you in reading and revising the topics, okay. So this is the question of IIT 2010, okay. So I hope this is clear to everyone, okay. Now the third method is a graphical method, okay. Now basically in a graphical method, graph would be given to you, okay. Different graphs are plotted like concentration versus time graph, half-life time rate versus time graph, rate versus concentration graph, rate versus time graph, and knowing the integrated rate law and the rate law, you can predict whether the reaction is zero order, first order, second order, okay. So I will just show you the example. We know that for a zero order reaction we write rate as K into A raised to power 0, okay. So we will directly say that the rate is constant and it is independent of the concentration. So if you plot rate on the y axis and concentration on the x axis, it will be a straight line parallel to the x axis because it is always a constant, okay. If we write the rate law, so we will write A T was equal to A naught minus KT, okay. So if you plot concentration of A with time, okay, so this will again be a linear graph with a negative slope having an intercept of A naught, okay. Similarly, if you write for T half is basically the time when 50% of the reaction is over, that is 50% of A has reacted, 50% of it would be left. So AT value would be A naught by 2. So when you calculate T half, it comes out to be A naught upon 2K. So in this reaction, T half is directly proportional to the concentration. So basically a plot between T half and concentration would be a straight line passing through a origin with a slope of 1 by 2K, okay. Similarly, you can plot for a first order reaction. So we know that for a first order reaction, rate is equal to K into A raised to power 1. So basically the graph between rate and the concentration would be a straight line passing through the origin with a slope of K. Now when we calculate the concentration of AT, so this is basically A naught into E raised to power minus KT. So if you plot concentration versus time graph on the x axis and concentration on the y axis, so it is basically a exponential decay graph, okay. Similarly, you can write the rate law as log of A naught upon AT is equals to KT upon 2.303. So if you plot log of AT, that is log of concentration versus time graph, so it will have an intercept of log of A naught with a slope of minus K upon 2.303. Similarly, we can calculate T half. T half we have already calculated it as 0.693 upon K. So basically T half is independent of concentration of the reactant. Okay, so it will be a constant that is parallel to the concentration axis. Okay, and we have already discussed average life. Average life is basically the reciprocal of half-life time period. Now for a second order reaction, it will be A raised power 2. So the concentration of, so if you plot rate versus concentration, so it will be a parabolic graph, and the rate expression of this was 1 by AT was equal to 1 by A naught plus KT. So if you plot 1 by AT versus T, it will be a straight line with an intercept of 1 by A naught and a slope of K. Similarly, we can find out the T half. Okay, so T half would be 1 by K into A naught. So it will be inversely proportional to the concentration. So it will be a rectangular hyperbola. Similarly, we can do it for a third order equation also. Okay, we can derive the integrated rate law. Okay, and we can also find the half-life time period. Okay, so if you look at the graph for a zero order reaction, okay, I already told you, because the concentration is varying, okay, linearly with respect to time, so the concentration versus time graph would be something like this. Okay, similarly, if you look for a first order reaction, for a first order reaction, we'll say that the plot of concentration, log of concentration versus time would be like a straight line with a negative slope. Similarly, if you plot for a second order reaction, the graph would look something like this. For a third order reaction, again, if you plot 1 by A square, 1 by concentration square upon time, it will be a straight line passing through origin. Okay. Now, if we want to plot T half, if we plot T half, that is half-life time period with concentration for a zero order reaction. Now, we know that for a zero order reaction, T half is directly proportional to concentration. So this is basically a straight line passing through the origin. For a first order reaction, T half is a constant independent of concentration. So this is a straight line parallel to concentration axis. For a second order reaction, T half is inversely proportional to A. Okay, so basically it is a rectangular hyperbola. For a third order reaction, similarly you can calculate T half is proportional to 1 by A square. So it is basically a hyperbola. Okay, so these are the plot that you can easily do. Okay, so you just write it down. Okay, I think this AT is basically equal to A naught minus KT. Okay, so the graph would be something like this. I think this is a wrong graph, so it will be something like this. Okay, just change this graph. Okay, because AT will be decreasing, the concentration of reactant would be decreasing with time, and it would get completed in a finite time. We have already done that. Zero order reaction gets completed in a finite time. Similarly, you can plot for first order, second order and third order. Okay. Now, if we plot half-life time period versus concentration of A, we know that it is directly proportional. For a first order reaction, it is a constant. For a second order reaction, it is directly proportional to 1 by A. So this will be a straight line. And for a second order reaction, it is directly proportional to 1 by A square. So if you plot with 1 by concentration square, it will be a straight line. Now if we plot rate, so basically dx by dt is rate with concentration. Okay, so for a zero order reaction, we know that rate is equal to k into A raised to power 0. Okay, we can write rate as minus dA by dt. A we can write as A minus x. So basically it will come out to be dx by dt, and A we will write as A minus x. So basically it is a independent of the concentration. Similarly, if we write for a first order reaction, so we know that rate is directly proportional to concentration of A. Okay, so if you write rate as minus dA by dt, A you can write as A minus x, because after time t A minus x is left. A is a constant, so differentiation is 0. So basically it will become dx by dt, and A is A minus x. So basically it is a straight line passing through the origin. Similarly, if we plot rate with concentration, okay, so basically it would come out to be a parabolic graph. Similarly, if you plot it for a third order reaction, so this is basically k into A raised to power 3, so this will come out to be a cubical parabola. Okay, so I hope these are very simple graph that you can easily make out. Okay, so graphical method is a very important method. Many a times questions has been asked on graphical method, so you need to know how to draw these graphs. Okay, and I hope you are comfortable in drawing the graphs because you might have done it in mathematics as well. Basically, we will be having 2 or 3 types of graph. One is rectangular hyperbola, one is normal parabola, one is a straight line y is equals to mx plus c format, and one is the constant graphs. Okay, basically we are dealing with these 4 kinds of graph. Okay, no higher level of graphs are required in chemistry. Similarly, if you look for the, if we plot dx by dt, that is rate with concentration, again it is constant. So if we plot dx by dt with a minus x, it is again directly proportional. If we plot dx by dt with a minus x square, so this will be again a directly proportional. If we plot dx by dt with a minus x cube or the concentration cube, it will be again a straight line, and the slope of like these 3 graphs would be equal to k. Okay, so this is how we deal in graphical method. So basically in graphical method we have to know the integrated rate law for 0, first and second order and third order reaction. Knowing the different integrated rate law, half-life, time period, we can draw the different graphs. Okay, and from these graphs we can easily predict which type of reaction is happening, whether it is a 0 order, first order, second order or a third order reaction. Okay. So now let's look at this question. This says that which of the following graph is not for 0 order reaction. So basically we are plotting T half with concentration. So we know that T half for a 0 order reaction is A naught upon 2K. So we know that T half is directly proportional to concentration. So this is the correct graph, this is not incorrect. X versus T. Okay. So if you look at a 0 order reaction, this is basically A changing into B. Okay. So at time t equals to 0, suppose the concentration was A, after some time t, X has been reacted, so this is basically A minus X and this is X. Okay. So we can write the rate law as minus dA by dt equals to K into A raised to power 0. Okay. We can directly bring A, because this is a constant, we can directly integrate and solve it, or we can put the value of A at time t. So this is basically this. Okay. So if you do this, so this is basically dx upon dt equals to k. Okay. So when you integrate this, this will become x equal to kt. So x is again directly proportional to t, slope is k. So again second graph is also correct. Look at the third graph. Third graph is basically dx by dt, which is also the rate. Okay. So that is again constant with respect to concentration. Okay. If you take log of A minus X and if you plot it with T, would it be a straight line? This would not be a straight line. Okay. Because the value of X is changing with respect to time. Okay. So the answer for this would be D. Okay. So this is a very basic question on graph. Okay. So look at this question. This was asked in IIT-JEE 2013. Just read this question. Again, it is a question based on graph. So this question basically says that there are 2 reactants P and Q. So suppose the rate is A with respect to P and B respect to Q. So it says that time taken for 75% reaction of P is twice the time taken for 50% reaction of B. So a data has been given to us that T3 by 4 for P is twice T half of P. So basically we know that this we have done in the previous lecture. I have also told you this is a very important conclusion. This is obeyed only in a first order reaction. We say that in a first order reaction, time required for 75% completion is always twice that of 50% completion. Okay. So this data basically indicates that the rate with respect to P is 1. The order with respect to P is 1. So the value of A in this case would be 1. Okay. So this line was written just for us to understand that its order is 1 with respect to P. Now look at the second part. The concentration of Q varies with time as shown in the figure. So if you look at the plot of concentration versus time, so basically I am saying this is decreasing linearly with the time. So obviously this is a 0 order with respect to Q, so the value of B would be 0, okay, because we know that Q is Q naught minus KT. This is the 0 order integrated rate law. So if you plot Q versus T, it will be a straight line with the intercept of Q naught and a slope of minus K. And because this reaction is going for completion, so obviously it is a 0 order reaction, okay. So the order with respect to P is 1, order with respect to Q is again 0. So the overall order is P plus A plus B, that is 1, okay. So this is again a typical IIT question, not difficult at all, but if you have the right conclusions with you, then this is a very easy question, okay. Now look at this question. This was in JEE Advanced 2018, okay. Just read this question. This is basically again a graphical question. This says that there is a first order reaction, A gas changing into 2B gas plus C gas at constant volume and 300 Kelvin. The total pressure at the beginning is P naught and after time T is PT, okay. So basically I am going to write this A gas changing into 2B gas plus C gas. So at time T equals to 0, we know that only A is present. So basically the total pressure is corresponding the pressure of partial pressure of A. Say after time T, some X pressure of it has reacted. So we will be left with P naught minus X. 1 mole of this is forming 2 moles of B and 1 mole of C. So the X pressure that reacted would form 2X pressure of B and X pressure of C. So we are just writing the equation in terms of pressure as we have demonstrated in the previous lecture. So the total pressure at time T would be the sum of partial pressure of A, B and C, because at this time the 3 gases A, B and C would be present in the container. So if you add this, so we are going to get P naught plus 2x. So basically PT is equal to P naught plus 2x. So x will be basically PT minus P naught by 2. Okay. So if we take P naught minus x, so P naught minus x will be basically P naught minus PT minus P naught by 2. Okay. So we keep 2 over here. So this is 2 P naught minus PT plus 2 P naught. So this will become 3 P naught minus PT upon 2. Okay. Now we know that this is a first order reaction. So we can write the rate expression. Okay. The rate expression I will write it over here. This will be KT equals to 2.303 log of initial concentration. Now initial concentration will be proportional to the initial pressure. So which is P naught upon the final concentration. Final concentration will be proportional to the final partial pressure of A, which is P naught minus X, which is also 3 P naught minus PT by 2. So this is basically 3 P naught minus PT by 2. So I will keep 2 over here. So this is the expression for this question. Okay. So basically now it is saying that initially only A is present with concentration A naught, and T1 by 3 is the time required for the partial pressure of A to reach 1/3 of its initial value. Okay. So basically if I want to calculate T1 by 3, I can say that T1 by 3 will be equal to 2.303 upon K. Okay. So basically this is saying T1 by 3 is the time required for the partial pressure of A to reach 1/3 of its initial value. So if the initial value was P naught, the P naught minus X should be 1/3 of it. Okay. Because it is clearly saying that it is the time required for the partial pressure to reach 1/3 of its initial value. The initial value was P naught. So after T1 by 3, the final pressure of A would become P naught by 3. Okay. So I will just write this as P naught upon P naught by 3. So I will get 2.303 into log of 3 upon K. So this is the basic expression for T1 by 3. Okay. So the correct option is R. Assume that all these gases behave as ideal R. So the first is ln 3 P naught minus PT versus time graph. Okay, so just have a look at this expression. Okay, so I can write this expression as, okay, I hope you have understood these portion. So I'm just going to erase this data. Okay, so if I write this equation, this is basically Kt equals to ln P naught minus ln 2 P naught minus ln 3 P naught minus Pt. So I can write this as ln 3 P naught minus Pt will be equal to ln 2 P naught minus Kt. Okay. So basically if you plot ln 3 P naught minus Pt versus T, it will have an intercept of ln 2 P naught. So this basically it is having an intercept, okay, and the slope would be negative. So this is the correct graph. Okay, ln, if we plot T1 by 3 versus A naught, now we know that T1 by 3 is independent of concentration. It's a constant value, K is constant, so it is basically the ratio of two constant. So this is incorrect. If you plot ln P naught minus Pt, okay, versus time, okay, so we have already said that there has to be a 3 P naught over here, so this is again incorrect graph. Now if you plot rate constant with A naught, okay, so if you plot rate constant with A naught, I think the graph over here was this, in the paper it was this, so this is not the graph. So if you plot rate constant with A naught, that is concentration. Now we know that rate constant is always a constant and changes only with change in temperature. So basically rate constant does not depend upon the concentration. So D is also the correct option. So the answer of this question is AD. Okay, so again a very simple question. So if you look at these questions, they are basically very simple. What do you have to do? You have to start from the scratch, from the very basic, from where the chapter starts. Have a very clear cut idea of all the basic theories. If you know the theory properly, if you have the idea of the theory proper theory, if you are knowing and you are reading a NCERT book, then things are very easy over here. But if you are missing out on any step, not building the basic concept, directly jumping on to the higher level problem solving, then that would create a lot of issue. Start from the basic as if you are preparing for your board exam. Start learning the very basic NCERT concepts, start using the formula, become more confident in using those formula. Once you have attained that level, then picking up to the higher level is very easy. Don't jump onto the direct difficult level question. Okay, these questions are not at all difficult, and like these are authentic JEE advanced questions. It is not that I am creating it and I am saying that okay these are JEE advanced questions. So if you look at these questions, they are basically very easy questions. Okay, I have already told you chemical kinetics is a very scoring chapter. Every year, 2018 you saw a question, 2019 you saw a question, 2020 hope the examination takes place in the month of July. So you definitely there will be a question on chemical kinetics. Okay. So then fourth method is half-life time period. Okay. So basically we are going to determine the experimental value of order of reaction through half-life time period method. Okay. Now for this, let us first derive the rate equation for a nth order reaction. Okay. So we are going to write a integrated rate law. Okay. So we are going to write integrated rate law for nth order reaction. Okay. So basically this is nothing but this is basic integration which we have to carry out. So suppose there is a reaction A is changing into B and we are saying that this is a nth order reaction, that is its order with respect to A is n. So we will write rate as K into concentration of A raised power n. So rate is basically minus dA upon dt. This will be equal to K into concentration of A raised power n. So we are going to bring A raised power n over here. Okay. So this is also equal to K into dt. So we'll integrate this at time t equals to 0. Only A was present, so we'll write it at A naught. After some time t, the concentration of A suppose is 80. Okay. So this basically we are going to integrate. Okay. I hope you are comfortable with integration. These are very basic integration. Okay. So if you integrate this, we'll get, I will write this as A raised to power minus n dA Okay, this is equal to k into dt from 0 to t, and this is from a naught to at. Okay, I hope how we are placing the limits is also like easily you are understanding it. At time t equals to 0, initially only A was present, so we are saying that its concentration is A naught. After some time t, the concentration of A is At. Okay, so when you do the integration of this, this will become A raised to power minus n plus 1 divided by minus n plus 1. Okay, so we are basically missing a minus sign over here. Okay, so this is what we'll get on integration. So we'll just adjust this minus sign. Okay, so we'll just adjust this minus sign. So this will basically will bring this outside because n is a constant. So this will become n minus n. Okay, so this is basically 1 by a raised to power n minus 1 at and a naught. Okay, so this is equal to k into t minus 0. So if you put the value, we will get 1 by n minus 1 equal to into 1 by at raised to power n minus 1 minus 1 by a naught n minus 1 equals to kt. So this is the equation for the nth order equation. Okay, so this is basically the nth order rate integrated rate equation. Just write it quickly. We will solve some questions on this as well. Okay, so I hope you have written this. So now let us quickly, I hope you have written this expression. So if we consider half-life time period for the nth order equation, okay, so we are just going to find out the half-life time period for a nth order reaction. Okay, so we are going to calculate half-life time period for the nth order reaction. Okay, so we know that at t half or the half-life time period, 50% of the reactant has reacted. That means 50% of the reactant remains. So the value of At would be A naught by 2. So if you just put the value of At as A naught by 2, so we'll get this as A naught upon 2 raised to power n minus 1 minus 1 by A naught n minus 1 equals to k t half. Okay, so we are going to get 1 by n minus 1 2 raised to power n minus 1 upon A naught n minus 1 minus 1 by A naught n minus 1, okay, is equals to k into t half. Okay, so we can clearly say that this is the expression of t half for a nth order reaction. Okay, so I hope you can integrate this easily. So one important and a quick conclusion that we can make from this expression is, okay, we will say that t half is equal to 1 by k into n minus 1 into A naught raised to power n minus 1 into 2 raised to power n minus 1 minus 1. Okay, so this is basically the expression for t half for a nth order reaction. So very clearly I can say that, okay, I hope you have written this expression or you can integrate it very easily using the integration formula. Okay, so we can write t half as inversely proportional to 1 by A naught raised to power n minus 1. So this is a very important conclusion which you should remember, which will make you solve most of the question very easily. We don't have to remember all these things, just only one conclusion if you are knowing, it becomes very smooth and very easy. So I can also say that t half is proportional to A naught raised to power 1 minus n. Okay, so I am basically saying that for any nth order reaction, T half is always proportional to concentration raised to power 1 minus n, where n is the order of the reaction. Okay, so just write it down quickly. Okay, so I am going to use this for the next method. So basically I am saying that the fourth method is half-life time period method. In this I am saying that T half is proportional to concentration of A raised to power 1 minus n. Okay, suppose the order is 0. Okay, for a 0 order reaction we will say that n is equals to 0. So T half will be directly proportional to concentration of A. We are just putting the value of n as 0. For first order reaction, we will directly say that T half is, okay, is independent, because when you put 1 over there, so it becomes A raised to power 0. For a second order reaction, we will say that T half is proportional to 1 by A. Okay, if you put n as 2, so this will become minus 1. So T half is inversely proportional to A. So if you take a third order reaction, so we will say that T half for a third order reaction, if you put the value of n as 3, so it will be inversely proportional to A square, concentration square. So this is the very basic idea. So if we can do the plotting as well, right, T half versus concentration will be a straight line passing through origin. T half versus concentration for a first order will be a straight line parallel to the concentration axis. T half versus A will be a rectangular hyperbola. T half versus A will again be a rectangular hyperbola. Okay, so I hope this is clear to everyone. Okay, so in this method we are basically going to have different half-life time period at different concentration. Okay, suppose a data has been given to us something like this, that say when the concentration was A1, okay, the half-life time period was T1. Okay, so we know that T half is always proportional to A raised to 1 minus n. Let the order of that reaction be n. So T half is always proportional to A raised to 1 minus n. So we will say that when the concentration of A1, when the concentration of A was A1, let the time half-life time period be T1. Now if we change the concentration of A as A2, let the time period be T2. So what we are going to do, we are again going to divide these two expressions. So we are going to get A1 upon A2, that is the concentration term, raised to power 1 minus n, equals to T1 upon T2. Okay, so if you take log on both the side, so basically we will get 1 minus n log of A1 upon A2 equals to log of T1 upon T2. Okay, so from here we can calculate the value of 1 minus n as log of A1 upon A2 divided by log of T1 upon T2. So the value of order of reaction can be written as 1 minus log of A1 upon A2 divided by log of T1 upon T2. Okay, so in the half-life time period method, at different concentration, half-life would be given to us. So we'll just divide them and we'll get the value of the order of reaction. Okay, write it down quickly. We'll solve some question on this as well. So just go through the today's lecture, because we have solved some JEE advanced level problems as well. So if you go through the lecture, if you remember all the formulas and how we are calculating the rate, then it will become very easy. Okay. You can either take a snapshot as well and prepare your notes after the class. So basically you have to remember this, T half is always proportional to concentration raised to power 1 minus n, where n is the order of the reaction. Okay, so at different concentration we will get the different T half values. On dividing it, on taking the ratio, we can get the value of order of the reaction. Okay. So just try this question. This basically says that the half-life time period of a certain substance is 50 minutes at a certain initial concentration. Okay, so let the initial concentration be C. So we'll say that T half, which is 50 minutes, is proportional to C raised power 1 minus n, okay, when the concentration is reduced to half of its initial concentration. So basically when we are reducing the concentration as half, okay, so the concentration will become C by 2. So this will be again proportional to the half-life time period, which is 25 minutes. So basically we are having two equations, we will just divide it. So this is basically, if we do 1 by 2, so this is 2 equals to C upon C by 2 raised to power 1 minus n. So this get cancelled out. So we get 2 equals to 2 raised to power 1 minus n. Okay, so we can say that 2 raised to power 1 is equals to 2 raised to power 1 minus n. So 1 minus n is equals to 1. So we will get the value of n as 0. Okay, we also know that for a zero order reaction, T half is directly proportional to concentration. So if you are reducing the concentration by half, time period, half-life time period will also reduced by half. Okay, so again a very simple question based on the half-life time period method. Okay, so in half-life time period method, you would be given different half-life at different concentration. Just frame a equation, take a ratio of them, and you can calculate the order of reaction. Okay. Now the fifth method is Ostwald isolation method. Okay. Now basically if you look at this, for reaction involving large number of reactants, this method was developed to determine order for such reaction. Suppose we are having a reaction something like this, A plus B plus C changing into some product. So we will say that rate of this is K into concentration of A raised to power, let the order with respect to A be A, with respect to B be B, and with respect to C be C. So this would be the rate equation. So what we will do, we will increase the concentration of all the reactants except one. Okay. So basically suppose we are taking B and C in excess. Okay. So what we will do, we will change the concentration of B and C and we will take it in excess. Now when we are taking it in excess, so the concentration change would be very small. So basically practically it can be taken as a constant. So that is what is written, concentration of all reactants was taken in large excess amount except that of one. Okay. So suppose we took B in excess amount, so basically this is B excess raised to power B into C taken in excess raised to power C. Okay. Now we know that because they are taken in excess amount, their concentration change would be practically, like the concentration change would not be much, so their concentration would be practically constant. So because this is a constant, this is again becomes constant. So if you multiply it with a constant, it becomes another constant. Okay. So suppose you are taking A1 as the initial concentration of A and you are taking the other reactants in excess. So whenever you are taking other reactants in excess, the concentration change is very small for the reactants taken in excess. So their reactants are taken practically constant. So basically this becomes constant. So this, if you multiply this, this would be the equation. Now if you take another concentration of A, suppose we take it as A2, okay, and we take B and C in excess because they are in excess. So we have taken care of them in the new rate constant, that is K dash. Okay. So just divide it, we will get the value of A. Okay. Similarly, you take A and C in excess. So when A and C are taken in excess, their concentration would be practically constant. So we can say that they are constant, multiplying with this constant would result into another constant, and the concentration of B can be varied. So you will get again two equations, just divide them, you will get the order with respect to B. If you want to calculate the order with respect to C, take A and B in excess. Okay. So because they are in excess, their concentration change would be very small and practically their concentration would be constant. So all of them are basically a constant. So you can replace this by another constant K dash, take the ratio of the two rate constants, changing the concentration of C, keeping A and B as constant, you can find out the order with respect to C. Okay. So this is basically Ostwald isolation method, where you are taking other reactants except one in excess. All the reactants that are taken in excess, the concentration is practically constant. Okay. The concentration change will be very small because they are taken in excess amount. So they are basically constant, so constant multiply with the constant becomes another constant. So we take it as a entire quantity as constant. So the only we are left with is one of the reactant. So basically we'll change the concentration. Suppose we take it as A1, A2, you just divide it, we'll get different rate at different concentration of A. On dividing we'll get the value of rate constant. So I hope this is clear to everyone. So just let's solve this question now. Now this says that some PS3 is introduced into a flask at 600 degrees Celsius containing inert gas. So basically PS3 is decomposing into P4 and hydrogen gas. So we have to balance this equation first. So suppose we multiply this with 4. So there is 4 phosphorus, 12 hydrogen. So we have to multiply this with 6. So a pressure data has been given to us. So also we don't know whether it is a first order reaction or not. So basically we'll say that at time t equals to 0, the pressure of phosphine was say P naught. After say some time t, X would have reacted. So this is basically P naught minus 4x, stoichiometry is 4, X would be formed, 6s would be formed. So the total pressure would be P naught minus 4x plus x plus 6x. So this would be P naught plus 3x. So we know the value of PT, pressure total. So we can calculate the value of x at 60 second as well as 120 second. Now let us look at the last data. It says that at time t equals to infinity. Now when this has reacted completely, we know that 4 mole of this will form 1 mole and 4 mole of this will form 6 mole of hydrogen. So basically P naught would form P naught by 4 and this I would get as 6 P naught upon 4. So the total pressure at t equals to infinity would be due to P4 and hydrogen because both of them are given as gases. So basically this is P naught plus 6 P naught by 4. So this is basically 7 P naught by 4. Now if we calculate this, because this value has been given to us as 276.4, but just see the beauty of the question. Now this question was saying that initially we were having phosphine as well as some inert gas. Now the inert gas was not undergoing any reaction, so that inert gas would also be exerting some pressure. So basically at time t equals to infinity, we are having P4, H2 and that particular inert gas. So that inert gas, suppose the pressure of inert gas is P inert. So the value have been given to us as 276.4. So we can calculate P inert because P naught has been given to us. P naught here is 262.4. The P naught is not 262.4. It is basically P naught plus pressure of inert gas. Because inert gas was present initially also. So the initial pressure of phosphine and the inert gas, the sum of them was 262.4. So if we look at this data also, we'll say that at this point of time at time t, phosphine is present, P4 is present, hydrogen is also present. So we'll also have inert gas over here. So we have to add inert gas everywhere. So we'll get these equation. You can get the value of inert gas P naught and X. We are having 3 equation, 2 unknowns. So we can solve that and we can get the value of inert gas pressure. And we can get the value of X. So once you get the value, assume it to be a first order reaction. So basically KT will be equal to 2.303 log of P naught upon P naught minus 4x, because the inert gas is not participating in the reaction, will not consider the inert gas in the expression. So if you put the value of time t as 60, you can calculate the value of at time t is 60 the value of rate constant. Similarly, you can calculate the rate constant at 120 second. If the value come out to be same, it is following a first order kinetics. If it is following a first order kinetics, you will get it as a first order equation. T half would be 0.693 upon K. So basically you can calculate the value of K from here and you can calculate the T half. So again, this is a very important question. Okay, so basically you have to read the question properly. Okay, if you miss out on one of the sentence, the question will become wrong. So this is basically saying that initially along with phosphine some inert gas was present. So in that inert gas was not taking part in the reaction, but it would be exerting some pressure. So suppose the initial pressure of this was P naught, finally it became P naught minus 4x. Okay, the pressure of this is x, this is 6x. So the total pressure would be P naught minus 4x plus x plus 6s. Okay, so that would be the total pressure at time t equals to say some time t, but there would also be some inert gas present. So we have to add the pressure of that inert gas. So this data was given to us as 272.9. Okay. Then we know that at time t equals to infinity, the entire reactant would have reacted. So this would change into 4 P naught by 4 at time t equals to infinity. Okay, and this would change into 6 P naught by 4. Okay, and at time t equals to infinity, again the inert gas would be present. So just add them. So this is basically the pressure at time t is equals to infinity. So we'll get the value as this. So using these equation, you can find the P naught x as well as P naught. Then just use the first order kinetics equation, calculate the value of K. If the K comes out to be same at different time, so basically it is a first order reaction. Okay, so this is a little subjective type of question. I am basically making you practice these subjective types of problem because they help you in doing a lot of calculation, and it actually helps you in building up the right concept, because this is not a preparation for any exam, this is a preparation for a particular subject. You need to be good in your subject, you need to focus, you need to enjoy that particular topic, then only you will be able to score. But if your entire purpose of getting taught or getting tutored is to get marks, then things would become difficult. Just forget about JEE, just forget about the advanced, think of a topic, you have to have a command on this topic, read a good book, do a lot of problem solving, like have a very good command in the topic and explore yourself. That is the way you enjoy the process, and the result is always going to be fruitful, and you are going to conquer in the exam. Okay, so this is it for today. So basically we have covered some very important concepts today, and we have covered some very good number of problems that came in JEE Advanced as well as some came in JEE Mains. So I hope you have enjoyed today's session. Okay, if you have any issues, you can write to us. If you have any doubt, you can write to us. Okay, so just go through the today's lecture, because we have covered a good number of questions today. So I hope that these lectures are interesting to you. So we'll definitely catch tomorrow for a new session. Thank you.